jokes about that horrible buzzing sound while I'm talking. Yeah, that's me. Anyway, so you probably saw in the program that we were talking about like things that I couldn't talk about. There's a little joke behind that. So when Steve first asked me if I would speak again this year, he asked me what kind of topic I would like to speak about. And there was a thing that I was working on for Firebase, which was built around Firebase and AI, but I wasn't allowed to actually tell anybody about it at the time, so he put that on the website as the abstract, and we never updated it. So there's an AI part of Firebase called Firebase Predictions, and so we'll talk about that a little bit later on this morning. So Steve asked me to do 2 talks. So the first talk I'm going to do is I'll talk a little bit about AI and mobile AI in particular, because after all, this is CodeMobile, and talk about the state of where we're at Google. I'm sorry, should introduce myself. My name is Laurence Moroney. I used to be on the Firebase team. I'm now on the Google Brain team. So I'm working on mobile AI in particular for Google and a technology, if you're familiar with, called Tensorflow. Anybody heard of Tensorflow? Okay, oh wow, most of you, good. So just to talk a little bit about AI and the state of the AI space and mobile AI. So first of all, nowadays, if you talk about AI, the first thing that you're probably going to see in the press, you know, what is AI anyway? The first thing you're going to see in the press is something like this, okay? Or if you don't see something like that, you'll see something like this. And if you don't see that, then you might see this or this. This guy gets around, by the way. Whenever you go searching for clip art, oh, I'm losing my... I guess we have a loose connection here. You know, so whenever you start talking about AI and you look at like news stories, I always have a picture, and like I say, this guy gets around. Or you might see an image like this, or this, or this, here he is again, or this, and there he is again. I guess if you're a robot and you're buff, people like taking a picture, or this. Or this. I don't know if this is the same guy and he's not wearing his clothes. Don't ask me. So, you know, or this really creepy one. You know, that kind of stuff. So it's like you talk about, like, as soon as you say AI and you start talking about AI, you know, these are the images that you start seeing in the press. And what I have to say about that is, nope, that's not AI. You know, don't worry, it's not about killer drones, even though we had one here just a moment ago. And so AI, that's nothing to do with this. It's nothing to do, you know, with these kind of robots and all these kind of things that you start seeing in the press when they start talking about it. But what is it all about? Well, another thing that I like to do is I like to start looking at, you know, how people are talking about it, in other words, other than how they have pictures about it. And then you start seeing things like this. You know, so it's like robots will destroy our jobs, and robots will take over most jobs in the next 30 years, and the rise of the machines. And I noticed that the top 2 of these links are from British newspapers, so I don't know if you're more paranoid in this country than we are. Just kidding. You're probably a lot less paranoid than we are. And but it's like, you know, nope. Nope, nope, nope. Okay, and then this one, of course, we always hear about AI as humanity's biggest threat. You know, as soon as I was actually having dinner last night in a restaurant in Chester, and then the waiter asked me, like, well, what are you doing here? What are you here for? And I said, hey, I'm doing a talk in the university tomorrow for this conference. And he's like, well, what are you going to be talking about? And I said, I'll be talking about AI and some things in development in AI. And then the man on the table opposite was like, AI, is that the killer robots? It's like, it's just amazing how much it's entered, like, the public perception about how it can be a really bad thing. And, you know, headlines like this don't help. And then this one is one of my personal favorites, where Adweek decided to do a search and replace the words artificial intelligence with the words demonic possession. And they started coming up with headlines like this one. My personal favorite is demonic possession now fits inside a USB stick, so watch out for those USB sticks, people. So it's, you know, it's amazing how much hype there is around AI, but it's also amazing how much it's misunderstood. And then there was another one, this one is one of my personal favorites. The biggest threat to artificial intelligence is human stupidity. You know, and I'm personally more terrified about biological stupidity than I am about artificial intelligence. Oh, and then there's also this one, and this one, to me, is a personal and quite an interesting story that we start seeing now, like headlines like CIOs must put AI on the fast track, and survey shows half of UK firms expect AI to transform their industry. So I want to rewind the clock 25 years to 1993. And so I grew up between Ireland and Wales, and I studied in Wales, and I graduated in 1991 from the university in Cardiff, which I'm heading down there tonight. And I graduated from there right into the middle of one of the biggest recessions the UK has had. Okay, at least up until that time, it was the biggest one in many years. There's probably been a bigger one since then, but that time was a massive recession. And I graduated, I had my degree in physics and computer science and couldn't get a job anywhere. You know, it's like I ended up working as a temporary clerk for London Underground, and I worked in a recycling company, kind of sorting cans out, for recyclable cans from non-recyclable cans. And it was a really, really tough time to be a graduate. It was a tough time to be anybody, but it was particularly tough to be a graduate because you'd spent all this time earning your degree, and now, you know, the only kind of jobs you can get are these dirty jobs. And then in 1993, we were in the middle of a massive hype cycle around AI. It was a lot like today. And at that time, the British government, and anybody remember who the Prime Minister was then? John Major, thank you. So John Major was the Prime Minister, and John Major did this, he ran this initiative to start seeding AI into companies in the UK without knowing really anything about what AI was. And there was a thing called HTNT, Higher Technology National Training. I don't know if that's still around. And John Major announced to the government that, you know, they were going to start this new initiative to put people back to work, to put people, particularly who were graduates who couldn't find a job, back to work. And they started this AI program, and they were launching this AI program and in the summer of 1993, and they wanted people from all over the country to apply for it. So I thought, okay, I'll apply for it, I'll give it a try. And they put us through like this battery of tests and all this kind of stuff, and I got in. I was so excited. You know, so I was finally off the dole, and I was able to like study something, and they were treating it as like graduate level studies, and it was under a scheme called NVQ. I don't know if you still have that here, National Vocational Qualifications. And they started up this program, and it was a company in Birmingham was running it. You know, after about 6 weeks, it closed down because they had no idea what they were doing. It was a case of it was like a lot of political capital being earned by saying, hey, look, we're starting with getting people off the dole, we're putting them to work, we're training them, they're going to be the next generation of AI people, and AI is going to transform industry. And then did that without having any idea what AI was, and then also when the hype bubble busts, then that training went away with it. So so when I start seeing headlines like this, I just feel history beginning to repeat itself. So no, that's not what AI is. And that's one of the things I want to talk about with you guys, and talk about, well, what actually is AI, and what is it from a developer perspective? You know, so what is it really? Can anybody guess? Well, it's a new coding paradigm. Let's just boil it down to that. Let's get rid of all the hype. Let's not think about drones and robots and jobs and all this kind of stuff. And let's just think about it. We're coders here. This is CodeMobile conference, and AI, it's a new coding paradigm. And you go, what? Okay, well, what about all the hype? You know, it's like, what about all these great things that AI is going to do? And like, what about all this artificial life and all the stuff that Elon Musk talks about? And it's like, nope, it's a new coding paradigm. And that's all it is. So what kind of new coding paradigm is this? You might think, from the hype cycle point of view and from the press point of view, that's kind of boring if we're just talking about coding. So what is it all about? Well, first of all, it's not really boring, and I actually find it something that's really exciting. And I'll share about why I think it's exciting, because it's opening up a whole lot of new ways to build applications and a whole lot of new scenarios for applications that you previously wouldn't have been able to do. But let's talk about what it's like from a coding perspective. Okay, so classical programming, something that we're all familiar with, something that we've been doing for many years. It kind of looks like this. You define some rules, you put some data into your program, and you get answers out. It's really as simple as that. Your classical programming, what we're all paid to do is we write rules in code, be it Java or Python or whatever. You know, that acts on data, and we get something out of it. So if I, for example, think about the simplest game that I can think about is noughts and crosses, tic-tac-toe, X's and O's, whatever you do, whatever you want to call it. So if you think about how would you write that game typically? Okay, so with noughts and crosses, right, you've got the grid like this, and you think about this in terms of like rules and if-then, and usually it's like, well, if the middle square is empty, you want to fill that with your piece, right? That's your first move. And then your second rule would be something along the lines of, well, if your opponent has 2 in a row, you want to block that, because if you don't, they're going to win on the next move. And then the third priority would be like, well, if the centerpiece is occupied and my opponent doesn't have 2 in a row, then I want to go in a corner. Right? Because usually the strategy of winning is you have one in the center and you have one in a corner. And those would be kind of the rules that you would be programming. A very, very simple scenario, very, very simple game. And the data, of course, is the representation of the board. So it's like, you know, there's X's here and there's O's there, that kind of stuff. So when I'm if-thenning on my rules, I'm if-thenning against that data. And that's a very simple scenario for classical programming. And I can build quite easily, I can write some code where a computer will at least be as good as a human at playing noughts and crosses. So very simple scenario, very simple rules to put into that. But what when you start getting more complicated, like chess? Okay, there are great chess algorithms out there, but there's a lot of if-thens that you have to start doing with that. And you want to look ahead because you can't just look at the next move that the person's doing, because a lot of strategy involves the move after, the move after, the move after, the move after. And then if you want to get even more complex than chess is the game of Go. And so this was the one that we focused on in Google when we've been researching how to do games and how AI works with games. And Go is an Asian strategy game. And a couple of years ago, an app that we wrote using machine learning beat the world champion of Go. His name was Lee Sedol. And since then, the app that beat Lee Sedol at Go, we've had another app using something called reinforcement learning and learn to learn that has been teaching itself how to play, and then it beats the app that beat him, and it beats him like beats that app 999 times out of 1,000. But like, think of all the rules with all these strategy that you'd have to build in. That's a lot of programming. Okay, that's a lot of debugging, that's a lot of testing. So machine learning and AI is a very similar paradigm to that. But instead of feeding in rules and data, you feed in answers and data, and then you get the rules out. And that's it. So all of the hype about AI and all the hype about machine learning is really just that. So instead of thinking in terms of the intelligence of the programmer writing code to determine the rules and acting on the data, what you do is you get lots and lots and lots of scenarios, and you feed in all of those scenarios, and then you start spotting patterns in that, and from those you start deriving the rules. So if you have enough scenarios, if you have 100 billion games of chess, for example, and you start feeding that in and start seeing the patterns, and you're saying, this is a win, this is a loss, and that's called labeling. So if you have billions of games of chess and you label, okay, this was white and this is where white won, this is white, this is where they lost, this is black, this is where they won, this is black, this is where they lost, then the concept of machine learning is instead of a programmer writing the rules for how to play chess, they are actually deriving the rules out of all of that data. So this has become huge again recently. We had that hype cycle that I mentioned 25 years ago, but this has become huge recently because of the intersection of processing power and big data. Processing power I'll talk about first. We all love games, and one of the interesting things was that the math that's involved in machine learning, there's generally two main areas of math. One is floating point multiplication and division, and one is matrix multiplication and division. And it just happens to be a massive coincidence that those two areas are huge in gaming, if you want to do 3D graphics and all that kind of thing. And as a result, GPUs have gotten cheaper and cheaper and cheaper and cheaper and cheaper, spurred on by gaming, of all things. And because of that explosion in cheap GPUs, meant that then there's now an explosion in cheap processors that can do matrix multiplication and floating point multiplication, and that's made machine learning explode because it's driven down the price. And then, of course, there's big data, accessing data, getting data sources, people generating data via IoT, and all that kind of thing. And these two things have intersected with each other to kind of spur on this new revolution around machine learning. But if you take nothing away from this talk, just take this diagram away, because that's what the revolution is all about. So classical programming, rules and data in, answers out. Machine learning, answers and data in, rules out. It's really as simple as that. Okay, so how does this fit in now with the overall scenario? How does this fit in with artificial intelligence and all these things? So the way we like to look at it at Google is like this, that artificial intelligence is a catch-all that contains machine learning, and machine learning has a specialized subset called deep learning, which I'll talk about in a moment. So if I talk about machine learning first, I can have a scenario of machine learning, like I'll try and demo in a moment, going back to noughts and crosses, where I built a simple Android application where I play noughts and crosses against this application, and this application does not have any of the rules of noughts and crosses whatsoever. It just knows when it wins, and it knows when it loses. So I will go, and as a human, I've played noughts and crosses, and I think about when I was a child, how I learned to play it. How do you learn to play? Nobody teaches you any strategy. Nobody teaches you anything like that. So if I play against it, and I'll go first, and I'll put an X in the middle, well, all the computer knows how to do is say, okay, I'm going to go to the first available spot, and it'll put an O in the top left. And then I'll put an X in the top middle, and it'll put an O in the top right. And then I'll put an X in the bottom middle, and I win, and it loses. So now that's a machine learning thing. So it now has, here's the board situation, and I lost when I did this move. So it's going to tag that. It says, this is a lost. And it will play again, and it will try something different. It will play again and try something different. And then after a while, I'll see if I can call up the video in a few minutes of this, even within like 10 or 12 games, it started learning. And it started actually exhibiting a behavior that we like to call emergent behavior, where suddenly that you're playing against this thing and it feels like it's alive. There's this behavior is emerging out of it. And this was, again, just data about playing the games. I didn't give it any rules. I said, this is a win, this is a loss. And it knew to try to veer towards a win and veer away from a loss. So that was machine learning. But there's a subset of machine learning called deep learning. And the idea of deep learning is just for more sophisticated scenarios where you have layer upon layer upon layer of learning. So let me give an example. So take, for example, I want to do a machine-learned algorithm in AI for determining the price of a house. So typically, this kind of thing is very difficult to do in rules-based programming because it fluctuates so much. I can't say, if house is in Chester and house is whatever square feet and house has this many bedrooms, it's going to cost this much. It's much more fluid than that. So, and as a result, prediction of house prices is something that wasn't really possible or wasn't very possible accurately under classical programming, but it becomes much more possible under machine learned programming. So consider this really simple scenario, okay, where I say, okay, I have 3 houses, and a 1-bedroom costs $150K, and a 2-bedroom costs $200K, and a 3-bedroom costs $250K. We can kind of figure out the formula for the price of a house from this, right? Can anybody see it? Right, it's 100,000 plus 50,000 times the number of bedrooms, right? Very, very simple rule for it. So, but when we start looking at this in terms of machine learning, I have a layer, I have an input data, and I have an output data. And this layer, this function in this layer is going to take in a weight. So this layer is going to operate on the number of bedrooms. And the number of bedrooms, I'm going to give it a weight of 50,000. And then the function within this layer is going to be 100,000 plus weight times the number of rooms. So this is a single layer machine learned neural network. Okay, very trivial one that will then give me the output that I want. But house prices aren't that simple. So for example, what if I say, and I start looking at like, okay, my real world data now says, hey, there's a 1-bedroom house costs $134K, and this 2-bedroom house costs $209, but then there's another 1-bedroom house costs $932K. It's like, I can't do a simple formula like a number plus the weight of the rooms because I didn't take into account location, right? So a 1-bedroom apartment in London might cost $932,000, or a 1-bedroom apartment in Chester might cost $134,000. So location becomes another factor into this equation. The size of the house, not just the number of bedrooms, becomes a factor into this equation. And there's a whole bunch of factors, a whole bunch of data points around houses become factors into this equation. And as a result, it's not feasible for me to draw up a rule anymore. But what is feasible is for me to determine a number of layers, and then on these layers give weight. And then I'll have one layer might be operating on the number of bedrooms. I'll have one layer will be operating on the size. I'll have one layer will be operating on the location. All of these kind of things. And that's going to give me some kind of an output. And then I have a function from that output, where I measure the loss. So I'll say, okay, I have layer, 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 and it's going to say predict that first house, it actually, from the first time through my layers, it says, that first house should be 170K, and that 9-bedroom house that was 900K should be 500K, just something along those lines. And that just tells me that I got a lot of loss, that the weights that I'm putting onto these layers aren't good. I put bad weights onto them, and as a result, the stuff that I'm getting out is really bad. And I'm comparing this with test data. Sorry, I forgot to mention that. So I train it with a bunch of data, and then I compare it with test data where I know the answer, and then I compare the loss of the test data against the loss of what my neural network is guessing the price of the house should be, and that gives me a loss optimization. And that loss kind of goes, nah, this sucks. Your algorithm sucks. Your weights need to change. So let's fiddle with the weights a little bit. What if we change the weight of layer 1 to this, and the weight of layer 2 to this, and the weight of layer 3 to that, and let's run it again. And let's take a look at our loss. And we go, yeah, you know what? Comparing my loss against my test data, I've only got I'm about 80% accurate. So my weight sucks, so let's do it again. And let's do it again, and again, and again, and again, until we get to the point where when we start measuring our loss, we end up, say, 98, 99% accurate. Like one thing that I've been working on recently is breast cancer data. So I can try to show it in a few moments where taking a neural network with breast cancer data and training it to the data that I have is the cells that have been taken from a biopsy. And I have about 6,000 data sets, some of which have been said to be malignant, some of which have been said to be benign. And then I go, okay, I'm going to throw all this data, and the data has things like the shape of the cell, the regularity of the shape of the cell, the size of the nucleus, and all these kind of things. Throw them into a neural network, set up a number of layers, set up the functions operating on these, saying, hey, you know what, the weight of the shape of the cell should be more important than the weight of the size of the nucleus, and these kind of things. And then start training that, and then testing it against a subset of data, which I know the answers for. It's almost like cheating on an exam where you look at some of the answers and then you try the ones that you don't know, until we end up getting a loss optimization. And even with 6,000 pieces of data, I ended up making it over 99% accurate in determining if I have a breast cancer cell, or if I have a breast biopsy cell, I should say, to tell if that is cancerous or not. It's become so simple to be able to do this kind of thing. It sounds a lot harder than it actually is. But this is the concept of machine learning, and this is what machine learning is all about. And machine learning is the key to AI. So it's really, you feed a whole bunch of data, you make a bunch of guesses as to the weights of each of the items in that data to the final answer. You get it wrong, you try again. You get it wrong, you try again. You get it wrong, you try again. And then frameworks like TensorFlow will get you, when you're getting it wrong and trying again, that you're not just doing something at random, it's going through a process called convergence to try and get it closer and closer and closer to the answer until you get a percentage that you like. And then your formula that comes out of it might be something like, the price of the house is, 50K plus 10K per bedroom plus, 5,000 per square foot, plus an additional 200,000 if you're in London, minus 100. This kind of crazy formula that might have 100 elements in it that a human would never be able to figure out. And it just comes from trial and error and trial and error and trial and error. A lot like playing the game. A lot like playing the game of tic-tac-toe that I spoke about. So that's the core of machine learning, and that's the core of AI. So, and this is what you end up doing when you do this then, is that you end up building something called a graph or a model. And this model is effectively a compiled binary blob that contains all of that intelligence. So if you are training a model, now you can execute on that model and you can pass data into that model and get the prediction or the classification back out of that model. So I should mention those two terms. So typically when you do machine learning and AI, it's two things that you're going to do. Number one is predicting something. So you want to predict a value like a house price or the trajectory of an airplane or something along those lines. And then the second thing is classification, where it's a case of you feed a bunch of data in and you want to see, is this a spam, right? Or is, I'm looking at an image, what is it? Or it's, like one that I've been looking at recently, it was like cameras in cities overlooking a city and then being able to tell if a building is in the early stages of being on fire. That would be a classification thing. So, and we found that from training lots and lots and lots and lots of data, you're able to determine a model that can see something before a human can see it. And I'll show a video about that in a moment of some plants in Africa called cassava. And it's just amazing what people have been able to do by training a model so that the model can classify things more accurately than a human can. So that's the framework that we have for this is called TensorFlow. It's an open source framework. There's a number of different programming languages you can use with it. It's primarily been Python, but you probably saw last week we announced Swift. So if you're a Swift developer, you can now start building TensorFlow applications and training models with Swift. But this is CodeMobile conference, so the first question would be like, hey, it's all very interesting and it's all very academic to talk about machine learning, but what about mobile? So mobile to me it's my passion in AI, and it's what I joined the TensorFlow team to work on. And the idea behind this is that we have a technology called TensorFlow Lite. And TensorFlow Lite it's a suite of tools, one of which is a runtime that runs on mobile, it runs on Android, it runs on iOS, and we just announced that we now have a runtime for Raspberry Pi for embedded systems. And it's a converter to the TensorFlow Lite format. So earlier I spoke about building a model. You'll generally build a model on a big supercomputer, or something with GPU or something with TPUs, and so that you can have the speed of training. The more data you have feeding into a model, the more training cycles that you do, the more accurate your model is going to be. And you get that model, which is a binary blob. Think of it almost like a compiled application. It's a set of compiled rules. It's really weights, within those nodes that I mentioned. But when you want to run that on mobile, then it's a case of that may not always fit. So we have a converter to do what we call freezing the graph. And so a graph tends to have thousands of steps within that graph for all of the checkpoints of training. But when we want to run it and we just want to do inference and we don't want to do training like you do on a mobile device, there's a converter. So that converter takes your graph and flattens the graph and freezes it and makes it mobile friendly. And we call that format TF Lite. And then there's an interpreter core that will run on device. And as it's running on device, then it's loading that model. In your application, you will take that data, you will send the data to the model will send you something back about that. Earlier when the drone was flying around and I was holding a banana up to the screen, there was a model on there which was for image recognition, and it's trained to recognize about 5,000 images, and I usually use a banana on it, but when it's running on the emulator on my desktop, it doesn't work so well. But the idea there is that's taking frames from the camera, it's taking those frames and it's passing that frame to the model, and it's getting back from the model, what are you looking at? And the model's saying, I think you're looking at a banana, or I think you're looking at something else. And that's what the interpreter core is all about. And then in addition to that, as mobile devices are getting more and more powerful, there's some operation kernels. So the idea there is that when you build a graph, there are a number of operations within that graph that are just standard functions, like there's a thing called relu, which is if the number is greater than 1, use it. If not, set it to 0. Oh, there's argmax, which is a case of here's a whole set of numbers, give me back the biggest one. And these are like just set of standard functions that are available in AI. So bless you. So made me jump. Yes. So those the number of those operations are in there. And if you start working with TensorFlow Lite now, a number of operations are missing because we're still working on it, and that's why I want to call it out in this slide. So some models will work, some will not. And now because, like I was saying, mobile devices are getting more and more powerful, then there's some delegates for hardware acceleration. In Android P, which hopefully we'll be talking about a little bit more later this year, there's actually some acceleration libraries for neural networks in Android P. And if you're using TensorFlow Lite to run your model on an Android P device, there'll be some hardware acceleration there where you can get even better performance out of your model. We've also been working really hard to make it cross-platform. So the flow, like we said, is you train your model on, I usually train mine on a desktop where I have an NVIDIA GPU because we support NVIDIA GPU. Or in the cloud, there's a thing called a TPU, a TensorFlow Processing Unit. So if you use Google's cloud platform, if you use like a virtual machine in that, they can actually use TPUs, which are processors that we've designed and built optimized for training. To be honest, you only really need to use this kind of thing if you're training on millions, if you're a professional, or if you're a university researcher or something along those lines. If you're doing something like what I did with the breast cancer data set, where I've only got a few thousand data points, I just did that on my desktop PC, which happened to have an NVIDIA GPU in it, and that allowed me to train it a lot faster. So you train your model, you convert your model into the TensorFlow Lite format, and then that TensorFlow Lite format, you can run it on Android, where we have a C++ API for Android, but we've been working on a Java wrapper, so Android developers like Java. On iOS right now, it's only the C++ API. I'm really trying to encourage some people to work on a C++ to Swift bridge so that Swift developers can start using it. And then on a Linux box or a micro Linux box like a Raspberry Pi, then there's a Python API, Java API, and C++ API, so you can start running inference on those as well. And if you're an iOS developer, any iOS developers here? Oh wow, most of you, cool. So we hear a lot about CoreML, and we really want to work closely with CoreML. So part of the idea is your binary TensorFlow model. If you run the converter to the TensorFlow Lite format, you can run it on TensorFlow Lite. But we've also been working on a converter to make it work on CoreML, so then you can use the CoreML runtime on iOS only. So when it comes to size, obviously size is very important when it comes to mobile. You don't want to be eating resources on a small device. So right now, our core interpreter is about 75 kilobytes. We've tried to shrink it and optimize it as much as we could. That grows with a number of different operations up to about 400 kilobytes. So the idea is if your model uses a limited set of operations, like some of the image inference models do, then you're going to be in the 75 kilobyte range. But when your model starts needing to use some of the non-standard operations and you want to add on to that, the actual runtime size can go up to about 400K, but it's still pretty small. So we've done that by keeping the dependencies really, really tight and doing something called flat buffer parsing. The idea with flat buffer parsing is that the model itself can be a very, very complicated mathematical model. So that concept that I spoke about of freezing it is to minimize the complexity of that model, and we call it flattening. So we have flat buffer parsing on there. So some of it may not be as accurate when it comes to the mathematical element of it. Like instead of being accurate to 50 decimal places, we're only going to be accurate to 3 or 4. You know, some compromises like that to be able to make it run on mobile. And this is how we've been able to shrink it down. So to talk a little bit about image detection, so with TensorFlow Lite, the first wave of this that we put out, that instead of just putting it out there and hoping for the best, we decided to take a look at some of the most common scenarios around machine learning. And one of the most common scenarios around machine learning, of course, is with image and object detection. So there are these things called mobile nets, and there's a model called Inception. And so what we wanted to do is we wanted to optimize TensorFlow Lite to make sure that it works with these. And mobile nets in particular, what they do is, of course, as well as classification, so like in saying that image on the top right is a dog, or landmark recognition to say, you know, those big black binoculars are the Google office in Los Angeles. It can also do things like object detection and counting. So here it's like on the top left one, it can see a bus, it can see a pedestrian, it can see those things. And it's the same technology that's being used in self-driving cars, as well as then in being able to, when it looks at a face, to detect that there's a face in the image, and then detect attributes about that face. It's smiling, it's frowning, those type of things. It's not about facial recognition, it's about facial detection. And actually the facial detection part was used by a campaign here in the UK about a year and a half ago by a toothpaste maker called Colgate. And what they did was, I think it was Colgate anyway, was they had a number of bus stops around the UK where, because they make toothpaste, they want you to smile. And you would go up to a booth at the bus stop, and if you smiled, it would detect that you were smiling, and it would take your photograph and give you like an Instagram-y type photograph, that kind of thing. And again, instead of somebody having to write lots of rules on an image to say, hey, I can detect an oval, and this lower part of the oval appears to be an upward curve, yes, that person's smiling, they were just able to train it on lots of images of people smiling. And that's, again, is like part of the paradigm shift that machine learning and AI is giving, that's kind of opening up lots and lots of new scenarios for developers. I spoke with a person from Coca-Cola. Last week we had the TensorFlow Developer Summit, and a guy presented from Coca-Cola, and he shared that they do promotion where they print like a number inside a bottle cap. And what they want you to do is, like, for their marketing, is like you hold your mobile up and you take a look at the bottle cap and you take a photograph of that number, and then it does image recognition on that number, and that's a unique number for that bottle cap, and you collect numbers and you get promotional points and all that kind of thing. But from a programming perspective, when you think about what it's going to be like, if there's a number of digits, first of all, if you've ever seen the digits printed on bottle caps, there's a lot of skew, there's a lot of things where, because it's a really rough dot matrix print, that even a human eye, I can't tell the difference sometimes between a 6 and a 9. And then as a developer, because this is circular, it can be rotated. So like if I'm taking a photograph of this, how do I know it's perfectly up? It could be rotated just by 2 or 3 degrees. And the skew of rotation, that from a classical programming perspective, just meant that the amount of code that you'd have to write was infeasible. But all they had to do was they had to print out tons and tons of these, label them, and then train a neural network to say, this one is number 1, 2, 3, 4, 5, 6, 7. This one is number 8, 7, 6, 4, 5, 3. And then rotate it at different, rotations, train it with those as well. And then as a result, with a whole lot less code than they would normally have to write, they were able to produce the thing that read the bottle caps. So it's like little things like that, or I'm wearing an Apple Watch right now, and the activity detection on the Apple Watch is really cool. Anybody have an Apple Watch? A few? Have you done things like running or rowing or any of these things? And it's really, really accurate at detecting that. And it's the same thing. Think about, how does it know if I'm running or if I'm driving really slowly, right? If you just go by the speed, and that's how that was one of the parts of the rules in the past with activity detection. It's like, hey, if it's between this mile an hour and this mile an hour, they're probably running. And if it's between this and this, they're probably biking. And if it's between this and this, they're probably driving. And it was all those rules that would have to be programmed in. But now they're just basically built with machine learning on the back end, where they just trained it with lots and lots of people. And I'm sure the data of me using it is being fed into Apple's model. So when I go and I say, okay, I'm going for my morning run, and I run, I've just given them an hour's worth of data of me running, so they can recognize what me running looks like, and then they can detect me running more accurately in the future. Those type of things, really, really cool, the scenarios that have been opened. But let's look at the code. So this is the code in Android, and how it will look in Android if you want to start interpreting off of a model. It's as simple as you import org.tensorflow.lite interpreter, and then you create an interpreter model. In this case, I call it TF-Lite. And so the model file, you just basically stick in your resources. It's going to be of the .tf-lite format. I'm just reading the back of the screen. Somebody just tweeted, "It's not about killer robots." Whoops. And so you load from your resources, you'll load that TF-Lite file, and then you'll also load the list of your labels. So what that means when it comes to machine learning is that, again, like if I have a trained neural network for spotting items, and I train that with a number of items, like mobile nets, I believe, are trained with, it's about 6,000 items. So say item number 575 is a banana. So what the mobile net's going to send back out to you when it detects something, it'll send you back, here's the probability that you're looking at item number 575, and then the label that attaches to that is banana. So as architecturally, it makes sense to separate them. So then if I'm not doing it in English and I'm doing it in Chinese, then I just do my labels in Chinese, and I would load my label list in then, and I can't say banana in Chinese, but it would be whatever that is. So, this is just your code. So you load in your labels, you load up your interpreter, and this is all you do. So you take your image data in. So in this case, I'll show a demo in a moment, but I'm capturing from the device's camera. The device's camera is giving me a whole bunch of frames. I'm taking those frames, frame by frame, I'm just setting up a byte array. That's my image data here, and I'm saying, TensorFlow Lite, here's my byte array, here's my labels, give me back a response. And that response will tell me something like this. Sorry if this is a little small, but this will look a little bit like, so you can see item 0 on the array here was the probability that when I was looking at this was like 8.44 times 10 to the minus 6. And item 1 was 1.79 times 10 to the minus 5. So it's extremely improbable that I was looking at these items when I took this photo. And if I go down here, so then at this point when I took this photo, item number 505 was 0.2 probability. Item number 504 was 3.8 times 10 to the minus 4 probability. So when I was taking the photo, when I was debugging, it's quite likely I was looking at item 505. It gave me a 20% probability I was looking at that, and that happened to be a coffee mug, and that's exactly what I was taking a photo of at that time. So let's look at this in action. So this is running on the emulator. So it thinks I'm a Dungeness crab. So, because I'm just running on an emulator, it's not the best. If you want to try it, I can show it on my phone later if anybody wants to see this. But if I hold the banana up, we can see it'll take a moment. It's 21% chance it's a safety pin. It needs to be trained. And it's seeing the reflection behind. Now it thinks it's a hot dog. But this is basically what's happening. That number at the top is how long it's taking to infer the image. So it's taking about 1.1 seconds on an emulator to infer the, there we see, now it's a banana, 68% probability it's a banana, that type of thing. So That's the mobile nets is running. This is TensorFlow Lite then loading in the mobile nets model, taking frame by frame from my camera and classifying what I have here. So it says, what was that? 38%. Now it's a pretzel or a remote control. So I can turn my TV on with this. If you ever watched the TV show Silicon Valley, there was a joke in Silicon Valley with the hot dog, not hot dog. That actually used the same code as this. So they use the mobile net models for that. Anybody watch that show? Okay, good. Hoping I wasn't being too irrelevant. All righty. So that's the idea of how all this happens. All this is open source, by the way, so you can download it on tensorflow.org. And that was actually my last slide in this presentation. So the whole idea behind this and what we've been working really, really hard to do is to democratize AI. So we've been trying to democratize it by bringing TensorFlow out so that anybody can build with TensorFlow. You can train models with TensorFlow. But we also realized that the power of AI and the power of machine learning can really, 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 really come to life when you start putting it on a mobile device. And I want to show a video. I'm also going to be showing it later this morning. But here's an example of in Tanzania, in Africa, there's a crop called cassava. And the cassava crop it's vital for the food chain. But the cassava crop is prone to disease. And if the cassava crop ever gets, horribly diseased, it can lead to famine, all those type of things. But one of the things that we learned was that it's very hard to spot early if a plant is diseased. And if one plant gets diseased, then of course that can spread the disease to the rest of the crop. And that can lead to disaster. And there's a lot of great innovation, low-tech, high innovation that the farmers have done, like in separating crops and all that kind of thing, so that disease doesn't spread. But they realized that one thing that was possible would be to actually use a mobile device and like an old cell phone and running a model. And the important thing is, like, when you're running the model flattened on a device, you don't have any cloud dependencies. So all of the classification is being done on device. What I was showing there was all done on the emulator. So instead of you taking an image and sending it to a big brain in the sky, and that big brain in the sky coming back and saying this is a banana, it's all actually being done on device. And if you're in the rural areas of Tanzania and you're trying to take a look if a cassava plant is diseased or not, of course you don't have any cloud connectivity. So they built this using TensorFlow, and I want to show a short video about it.
Cassava is a really important crop. It provides for over 500 million Africans every day.
When all other crops fail, farmers know that they could rely on their cassava plants to provide them food.
There are several diseases that affect cassava, and these diseases make the roots unedible. It is very crucial to actually control and manage these diseases.
So we're trying to use machine learning to respond to those diseases.
And TensorFlow is the best foundation for our solutions. The app that we've designed can diagnose multiple diseases. It's called Nuru, Swahili for light. The light that farmers can use to see their problems and find solutions. You wave your phone over a specific leaf, look at it, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, we have an option for you to get advice and learn about the best management practices.
The object detection that we use through TensorFlow relies upon our team annotating images.
We've collected over 5,000 high-quality images of different cassava diseases for this project. We use a single-shot detector model on a mobile net architecture. It's able to make predictions in less than 1 second.
Instead of having to implement thousands of lines of code, TensorFlow provides a library of functions that allow us to build architectures in much less time.
We need something that can be deployed on a phone without any connection. TensorFlow is able to shrink these neural networks to be able to fit on your mobile device.
The human input is absolutely critical. We're really building something that augments your experience and makes you better at your job.
So with AI tools and machine learning, you can improve the yields, you can protect your crops, and you can have a much more reliable source of food.
AI offers the prospect to fundamentally transform the life of hundreds of millions of farms around the world.
you can see a product that can actually make someone's life better. This is kind of revolutionary.
So just to wrap, it's a new programming paradigm. That's really what this is all about, and it's a new programming paradigm for mobile. I think it opens up a whole bunch of new scenarios that you can take advantage of as a developer. You may not be building for Cassava, you may not be building for Go, but there are so many new scenarios that are just out there that weren't possible before, and we think AI and machine learning on mobile will make that possible. So forget the hype and think about what you can do and think about what you can bring to mobile development. And with that, I just want to say thank you. We'll take a short break, and then we're going to do a talk on predictions in Firebase. So thank you so much. At the front here?
Yes, I'm working with some character images.
Okay.
And about mobile vision.
Yep.
Is ever like going, oh, cool, thanks. Is it planned to be ported to iOS? Because mobile vision on iOS only offers a limited subset of features, and like OCR is not among this.
Yeah, so the question is if character recognition is going to be ported to iOS. From a AI, I almost said IO, from an AI perspective, with TensorFlow Lite is working perfectly fine on iOS. It's a first-class citizen for us. So if you are training based on a character recognition model like MNet, then the idea is it'll work just the same as it does on Android. We also have character recognition libraries in Android. Those ones are totally separate thing. That's an Android initiative, and as far as I know, there's no plans for that to be ported to iOS, but the technology for you to be able to train yourself for character recognition is. And the most common one for handwriting characters is called MNet, and we actually test it very extensively with MNet. So, all right, thanks. In the white here? Oh, I'm sorry. Yes, sorry.
That's all right. I just had a quick question about you were talking about the hardware acceleration support in Android P.
Yep.
I'm just wondering if there's going to be support library version for that. Support library support for that, and if so, what level of support library?
I'm not allowed to talk about that yet.
Okay.
Google I/O is coming up in a few weeks, in like May 7th, 8th. We'll be making some announcements then about Android P. Cool. Sorry. Can't jump the gun, I'm afraid.
Hi. I'm not sure if I missed it during the thing, but I think you said the training was done typically on a more powerful GPU-based machine, I think.
Yep.
But is there the ability to do some training on the device? So using TensorFlow Lite on the device, can we go around Chester University, rather than just doing the data capture and then feeding it in later, can we, on the fly, do some training?
As of now, no.
Right.
As of now, TensorFlow Lite would be the inference runtime. Training would be done on TensorFlow, not TensorFlow Lite. And TensorFlow doesn't run on an Android or iOS device, only TensorFlow Lite does. If you're using a lightweight device like a Raspberry Pi, then TensorFlow will run on that. So you could do training on that. But it's not nearly as convenient, of course, as doing it on a device. Right now, the device is primarily the runtime. All right. Was the one on this side? Yeah, at the back.
Once you've trained a model, how do you know why it's making a decision? So you know the decision it's made, but how do you know why it's made that?
You can inspect the graph using something called TensorBoard. So if you saw that animated video that I was looking at there, so you can actually see the flow of the data through the graph on that, and you can from that extrapolate why, as in which layer has which weight and which is important, that kind of thing. But typically the why is more done from the loss function. So you can say, okay, if I have this model with this set of checkpoints, I'm 99% accurate. If I have this model with this set of checkpoints, I'm 94% accurate, and I can compare my models to see the why there. But very often the reason is more, you got to be very careful with your training and test data that they're perfectly random, that you haven't introduced bias from your data. I mean, I'll give a classic for me when I first started doing the breast cancer one. I just trained, I put the data in top down, and the top of my data was all benign cells, and the bottom of my data was all malignant. And I was training it to spot benign cells, and I was testing it against malignant, and I was getting like 20% accuracy, which is really bad because it's supposed to be 2 things, so it should be at least 50% accuracy. So it's things like, it's managing your data is a very important part of it, and testing with different types of data, making sure that it's randomized, making sure you're not introducing bias in your data, that kind of stuff. And you can use the tensor board visualization to really help in that. So, time for one more? Nope. Oh, yeah, over here, sorry. Sorry with these lights, it's hard to see.
Yeah, just so when you were doing your learning with the 6,000 data points for the cancer stuff, how long was that taking to run? You said you did it on your own desktop with the GPU.
Yeah, it's just a few minutes is all it took, because it was only a few thousand. So running on, it's an Alienware gaming desktop that I wiped Windows off and I put Linux and TensorFlow on it. And then TensorFlow, we have 2 forks. One is TensorFlow, one is TensorFlow with GPU. I put the one with GPU support and I trained it with those few thousand. It only took a couple of minutes. It really doesn't take long because it's not a lot of data. All right.
Perfect. Thank you very much.
All right, so we'll take a quick break.
Yeah, no, we're gonna come back and do a couple of other things. So big round of applause. Thank you very much, Laurence.
Thank you. Thanks.